If you remember in the last video, which was basically an introduction or more like a game plan for how we're going to study, these were the steps we were going to follow to formulate our theory of kinetic model of matter or the particle model of matter. So in this video, here's what we're going to do. We're going to ask some fundamental questions and we're just going to leave it at the postulate so you have something to go back and think about. All right. So what fundamental questions do I acquire from nature from just observing my surroundings? First of all, the thing you have the most access to is air and water. Now you ask yourself, water is sort of a weird thing. I don't really understand how it works. Now assume that no physics has ever been taught to you. And besides that, you have very little pre-existing knowledge, most of it from observation. Now let's talk about the changes of states. Now these basics, if you don't observe them, you're never going to make any progress in physics. First of all, you think to yourself that, okay, so basically what I understand around me is continuous stuff, but I see that ice becomes water sometimes and water becomes steam. And I have no theory, no underlying principle to really understand how that happens. So the first thing that I want is some theory to basically understand what is actually going on over here. What is making this happen? What I know though is when I have a hotter climate or I have a larger value of temperature, this becomes something that happens more quickly. Now that means that it has something to do with temperature. And I have some intuition in me that whenever there is more temperature, there is more energy. How do I think about that? Well, I think about heat. When things are hot, basically we think of them as having more energy, right? Some of you might have that intuition. The other ones of you might think of it like this. If I have a heater and I put it near this ice cube, well, what is that heater doing? It's taking my electrical energy and it's supplying it somewhere. And that supply is making this melt or maybe evaporate or boil. And these two terms are actually different. Evaporation is different and boiling is different. And we're gonna talk about them later on. But right now, I do understand that some corresponding energy or temperature relation exists. I'm going to see that qualitatively. I mean, we can generally talk about boiling points and melting points, but those aren't technically relationships or equations. Then your brain goes berserk. It's going to ask you questions like, okay, this is not the full story. There has to be a structure that is making this up. So what you want is substructure of matter. That is called reductionism. This is not something the O-level syllabus is going to demand, but being a physics student, you should know about it. Basically, reductionists are really curious people who think that every structure is made up of a substructure. To every bigger picture, there is a smaller picture. Now, many questions are going to arise. Smaller ones, actually. Curiosity. Why is it that I am sitting in one room and I can smell the perfume from another room? I'm not going to do that with water or rock, am I? Rocks are not going to be that accessible to my nose. So, what's going on over there? What is the defining difference between a perfume vapor, rocks, and water? There is difference. I know, but I haven't formulated it yet. And over here, we are assuming that we have not studied the states of matter. And now we're going to question that how does the structure of matter interact? So reductionists and all other people do think that if the perfume as a large in a bigger picture is going to interact with me, then why is only the bigger picture considered? We should ask that the smaller structure of matter is going to interact with each other as well. And what is that interaction going to be? What is that interaction going to be like? So I have written these two processes: diffusion, we will consider that an experiment and arguments, and Brownian motion. Now, one more question that is purely based on observation. Okay, before we move forth, I'm going to be using the words solid, liquid, and gas, and I haven't touched on the states of matter yet. So, whenever I use those words, think of that as water, ice, or steam. Okay, back to the topic. What was I so confused about? These bars. Let me explain what that means. So, basically, you're curious people that have no ability to really understand or perceive science and physics, but you can make observations. A thermometer is given to you, so basically, okay, you don't know science, but you have a thermometer. Wow, how funny. So you put a thermometer in an ice cube that you just got out of the fridge. Now this ice cube is a solid. You supply it somehow with constant heat. You give it a source. You put it in something called a heat bath or a water bath. Now we can talk about what a water bath is and what is its experimental importance, but maybe in another video. Right now think of it as a constant heat supply. So you start heating it and you understand, okay, I'm heating it and the temperature is rising. Okay, I understand. Fine. you start to see very, very close to 0 degrees that, hey, this solid ice is actually becoming a liquid and it looks like water. But oh, I did not explain the axis. Okay. So basically, you have temperature on this axis and you have energy on this axis. You shouldn't actually put energy on its axis, you should put time. So what's happening? You're giving constant heat, and with time, the energy supplied on the ice cube is increasing. So you put an axis, and you want to measure how temperature is rising. And remember, we have this intuition, this crazy intuition about energy and temperature, that more energy, more temperature, or something like that. Something really crazy happens here at 0 degrees. Even though energy is being supplied, there's no rise in temperature. So basically, I have a cube, and then because of the energy supplied to it, it's melting. But it's not increasing in temperature, and I'm being inclusive here. The water's temperature is 0 degree, and the ice cube's temperature is 0 degree. So at 0 degrees, which would henceforth will be known as the melting or the freezing point of water, you're providing it with energy. The ice is converting into water, but the temperature, for some reason, neither increasing nor dropping. But then, when all of the ice cube has been melted and become water, you see that the temperature is rising again in its liquid form. So basically, your temperature is following the intuition. You give it energy, or you give it something that supplies energy, and you measure time. So after a set amount of time, you get set amount of energy supplied to this water, and the temperature is rising. Sure enough. And again, although you're seeing steam rising from it, but there's this fixed point, 100 degrees in Celsius form. I haven't talked about absolute temperature yet. 100 Celsius, where there seems to be no difference in temperature. Energy is being provided. You can see I'm providing energy. Basically, I'm putting loads of energy into water. It's converting into steam, but the steam's temperature is not greater than 100 degrees, nor is the water's, even though it's absorbing energy. So, what is happening? And then you see gas. And somehow, okay, let's imagine you can take its temperature, and you take its temperature, it's rising, and okay, it can rise from here and out. These dashes, these are also in our fundamental questions. So here's what we're gonna do. We're gonna set up with certain assumptions that don't look crazy to us. The average reductionist is gonna say matter is made up of particles. And we're gonna assume that these are small spherical balls, these particles. So this can be atoms, ions, compound structures, molecules. We'll all consider them as particles, as small spherical balls for simplicity. So homogeneous stuff, if you know about what homogeneous stuff is. Okay. Then we are assuming that they are in motion. And why would you think that this is not crazy? Well, think about your perfume example again. The scent of the perfume is coming from the other room to your nose. So there has to be something moving, right? So they are in motion. So here's what you have basically come up with. You have come up with discreteness, that instead of being smooth and continuous, matter is made up of smaller things. And secondly, you have come up with motion, and this one is just a little bit crazy. The rate of motion, or basically the velocity of those particles, those spherical things, okay? The velocity is basically how they're moving. This increases when you add energy. And okay, why would you believe that? Well, some of you know about the kinetic energy and potential energy, right? So if you're putting energy into something and you believe that it's made of these small things, either their potential energy should grow or their kinetic energy should grow. But let's talk about potential energies, for example, gravity or in springs. Only changing the object's position is what gives them or takes away the potential energy. And I've been talking about energy as basically heat. So temperature or heat isn't going to affect the potential energy. So energy is basically giving them kinetic energy, and kinetic energy means that the velocity is increasing. You get that? I hope you do. Okay. And because the velocity is increasing, temperature is increasing. Well, you can see from this graph, whenever energy is increasing, roughly temperature is increasing. There are these blocks where this relation doesn't hold. But then again, we do see that energy increasing means temperature increasing. And if velocity increasing is because of energy increasing, that means velocity increasing is the same as temperature increasing. They are equal things. For example, you have more violently moving particles, that means the overall temperature is going to be higher. If you have less violently moving particles or less velocity particles, you're going to say that, okay, the overall temperature is going to be low. Now, I've cut this postulate because this isn't a postulate. We're going to move on to claims next, and we're going to see that this is just going to emerge from these because we are going to apply some heavy critical thinking. But we can talk about these two things, that there is a dependence between velocity. Say velocity is directly proportional to temperature. Well, no, it's not going to be that simple. And in advanced physics, you're going to see a lot about this. What is the dependence of velocity and temperature in different material? When we talk about this force, we are going to talk about why the perfume is moving through the rooms and the rock just stays there. there has to be something holding it together. So that is going to give forces as an emergent property. Emergent property is a very special term, a very special jargon in physics, and I'm not using it that way. But you have to understand, because of a lack of a better word, I'm going to use it. So, co learners, I hope that you learned something from me today, and actually, I learned something explaining this to you. So, remember, I'm not your teacher. We are co learners and co teachers. Thank you for watching the video.